Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 30 of this course on machine learning for earth system science. We are still in module 4 where we are studying how machine learning can be used for remote sensing for basically machine learning can be used for earth observation systems, that is to say remote sensing. The topic of this lecture is image segmentation for remote sensing. So, what we are going to cover today are different applications of image segmentation in remote sensing and how machine learning approaches, especially deep learning, can be used for such image segmentation. So, image segmentation is originally a task in computer vision or image processing if you want to call it. The task is, as the name suggests, to divide an image into multiple parts. But if we want to do semantic segmentation, then basically each part should mean should be defined in terms of the objects present. So, in other words, every pixel of the image, they can be assigned to certain or like we can imagine it as some kind of a clustering of the pixels where two clusters where two pixels that are associated with the same object can be considered to be as part of the same cluster. So, like if you look at this image, for example, you can say that so this is originally an image of a dog and 3 sheep running on a field. So, here if you see, it's like the semantic segmentation shows all the pixels which are associated with the sheep. They are coming in the same cluster as indicated by the blue color. All the pixels that are associated with the dog are coming in another cluster as indicated by the red color, and finally all the pixels which are associated with the field, they are coming in another cluster which is the green color. So, similarly, apart from semantic segmentation, there is instance segmentation also, where each of the instead of considering all of these as the category sheep, we can consider these as individual objects, and basically we are doing something like individual object segmentation. So, it is essentially a pixel labeling task where each pixel has to be either clustered or classified according to certain class labels if they are known beforehand. The catch is that the adjacent pixels are most likely to either belong to the same cluster or have the same label, because all the objects are known to be contiguous things. Like usually 2 pixels that belong to the same object should come in the same cluster or they should have similar labels. Now, in case of remote sensing, one standard application of this kind of image segmentation is in LULC mapping. That is, LULC stands for land use and land cover changes. So, basically here the task is each pixel has to be classified according to the type of land use, that is it like does that pixel cover a forest or a building or a road or a water body or what. Now, the challenge here is that in top view optical imagery, it is very difficult to obtain the feature representation of the different classes. Like when we are taking a lateral view like this, we can see a clearer view of the or we get a bigger view of the object we are interested in, so that it becomes easier to recognize it. But when we are taking the top view, then only a small part of it is visible, and from the top we may not have get enough information to identify what class it belongs to. And we earlier talked about different kinds of imagery or satellite imagery which we may get in remote sensing: hyperspectral, multispectral, infrared, and the SAR and so on. Now when it's if it is in non-optical imagery, then this problem becomes even more challenging, like partly because of the absence of or because getting the ground truth also becomes very difficult in that case. I mean, if it is a RGB image which is in the visible spectrum, then we can expect a human assistant to actually label the different pixels, so for the purpose of training the neural network. But if we are considering a SAR image which a human on seeing it will not be able to interpret it, then the task becomes even more difficult. Now so like in the literature of computer vision, several kinds of algorithms or models have been developed for the task of segmentation. I mean, segmentation of normal images like this one, not necessarily for remote sensing, but they are still image segmentation approaches. So it might be possible to borrow them in the when we are dealing with remote sensing. Now this earlier this remote like in the pre deep learning days, this image segmentation often used to be done by graph based methods. That is to say, every pixel was considered as like as a node of the graph, and then two pixels which like whose intensity values were similar, like an edge was drawn between them and so on, and then the task was to look for connected components in such a graph. Like this was largely the approach in the let us say around 2010 or so. After that, some latent variable based approaches also came, where with each pixel one we considered a latent variable which indicated its cluster membership, and then the something like a Gaussian mixture model, these kinds of things were done to estimate the or to infer the values of those latent variables, along with the constraint that adjacent pixels are likely to have the same values of the latent variable, somewhat similar to the graphical models which we had discussed earlier for extracting spatial patterns of Indian monsoon and so on. But now we have deep learning, and now the idea is to like use these kinds of neural networks to for the purpose of image segmentation. Now two neural networks that have been two architectures that have been particularly successful for this task are the SegNet and UNet. Now both of these SegNet and UNet, so which are shown here, both of them are essentially based on the idea of like first downscaling, I mean reducing the spatial resolution, and then upscaling, that is increasing the spatial resolution. Now in a CNN, as we know, this kind of reducing of the spatial resolution can be done by pooling, while the spatial resolution can be increased by unpooling. Now why do we do the pooling to reduce the spatial resolution? Because basically the task is that of coarsening the image, that is, we want to throw away the excess information. We do not really care about what is the exact value of these pixels as long as they lie in the same object. Rather, we would like to get a coarsened view of this image, so that like a pixel, and so that like in the coarse representation, if two pixels have similar values, we will understand that they probably belong to the same object and need to be placed in the same cluster. But so basically the purpose of this coarsening is to throw away the local the local variations and preserve only the major or the global variations in the pixel values. And of course this is to all this while assuming that the different classes or the different clusters they have their characteristic pixel values. If they did not have, that is to say, if there were two objects that two different objects but having the same color or having the same shape, etc., then we may not be able to separate them. Say for example, if we had say a green snake on a green field, then of course we will probably not be able to separate, because like on the basis of these RGB values there is not sufficient information to separate it. Now once the pooling has been done, the image is reduced to a low resolution for the purpose I mentioned above, but then I want the output to be in the same resolution as the original image. So, I do the unpooling, and which is aimed at increasing the spatial resolution back to the original resolution, but without restoring the all the details. However, when I am doing the unpooling, I need to get some information from the previous steps. I mean, that is when I am coming back to going from the low resolution to a lower resolution to the higher resolution. In a sense, I have to bring in some extra pixel values. So, how that will happen? So, for that to happen in a consistent way, we need these kinds of skip connections. So, like as you can see, these skip connections are present in UNet also. So, it is like the pooling is the downscaling is done in several, we can say in several steps, and in the upscaling is also done in the same number of steps, and these skip connections basically connect the same levels. So, like as you can see, like the second level of pooling is like linked to the first level of unpooling. The first level of pooling is linked to the second level of unpooling, and so on. So, this helps to obtain an image like this, which is in the of the same spatial resolution as the input, but like with this kind of clustering like with the pixels clustered. So, as you can see in the output image, most of the pixels have like adjacent pixels have the same value, indicating these kind of clustering, but this clustering is consistent with the input image. So, like the example which we are seeing here is like the input is something like a city view taken from the top, and the output is the land use land cover map of the city, that is showing the buildings, the roads, the grassland areas, etc., in different colors which indicate different clusters. Now, we will see several examples of how this approach can be used for to answer various interesting questions that on the basis of this remote sensing data. So, there was one competition called Deep Globe 2018. It was something like a challenge that aim was to parse the earth through satellite images. That is, satellite images are captured from different places all over the world, as we see in Google Earth and so on. The task was, first of all, road extraction, that is given a city map like that is given a city image like this, identify the major roads. So, as you can right away understand, there is a long highway kind of thing, like this structure is probably something like a large highway, but there are also various other long like avenues or busy roads or narrow roads, lanes, etc. Like, so the aim here is to like build or identify the road network of the city. Now, like these road will not come out immediately because of the presence of many other things also in this satellite image, all the buildings, the lakes, the parks, everything. So, I want to segment the image in such a way that I can like extract all the roads. That is one challenge. The second challenge is building detection. That is, again, now we are the same, let us say we are focusing on the same city, but I want to identify each and every building. So, so basically that is another image segmentation. So, like all these purple blocks you can see here on this image, if you take a closer look. So, each of them are supposed to represent one building. The third one is land cover classification, that is, I want to identify which pixels cover buildings, which pixels cover some fields or vegetation, which pixels cover a river, and so on and so forth. And now, so as a response to this challenge, various researchers submitted like various machine learning models, deep learning architectures, etc., for solving specific parts of this problem. So, like one of these is related to this identification of ground material. So the different ground materials might be say forest or greenery, that is to say basically vegetation, then sand, clay, concrete, asphalt, etc. That is the so these are different kinds of materials with which the ground is built. So like can we from the remote sensing image can I identify? So for example, this is a remote sensing image, satellite image. So as you can see, this is probably water. Here we see vegetation along the water or along the coastline. We see a sandy region. Then apart from that, there are some built regions which have which are made of concrete, so and so on. So like the output is to build this kind of a map where each region that is made of one particular material, that is placed as one cluster and hence marked in one color. So this is again done using a like something similar to an UNet only. The only thing is that instead of having a single UNet architecture, there is a stacked UNet. That is like there is one UNet which produces an output, then that same UNet the output of that UNet is then again passed to another UNet, then further another one more round of UNet and so on. So you can call it as something like a nested UNet architecture. So the one UNet is suitable for one round of image segmentation. So if we stack it, so we can still further segment the different images, these things. Okay. So like these are some of the results which they have obtained. So in different parts of the images of the satellite images, if we focus on them, they are getting the different spatial maps and so on. Another task is was that of this is for skyscapes. This is especially for aerial scenes over a city. So understanding the complex urban infrastructure with centimeter level accuracy is essential for many applications, from autonomous driving to mapping, infrastructure monitoring and urban management. Aerial images provide valuable information over a large areas instantaneously. Nevertheless, no current dataset captures the complexity of aerial scenes at the level of granularity required by real world application. To address this, we introduce skyscapes, an aerial image dataset with a highly accurate fine-grained annotations for pixel level semantic leveling. Skyscapes provides annotations for 31 semantic categories ranging from large structures such as building, road and vegetation to fine details such as 12 subcategories of lane marking. We have defined two main tasks on this dataset: dense semantic segmentation and multi-class lane marking prediction. We carry out extensive experiments to evaluate state-of-the-art segmentation methods and skyscapes. Existing methods struggle to deal with the wide range of classes, object sizes, scales and fine details present. We therefore propose a novel multitask model which incorporates semantic edge detection and is better tuned for feature extraction from a wide range of scales. This model achieves notable improvement over the baseline in region outlines and level of details of both tasks. So like this is what the model architecture basically looks like. It's a very complicated model with various modules in the model, and so so basically this is the image, and which is based on a series of sequence of convolution image neural networks like this. So as I said, it's a multitasking framework in which in different so these are the different modules for the multitask thing, and so the overall thing, this is what it looks like. So these you can see these FDB, LKBR, FRSR, etc. written here. Now these are all modules, and these modules, they are individual, their specific networks are actually shown here. Like LKBR, it's it's a neural, it's a CNN with two separate branches, and these two branches are later fused together. And similarly the FRSR, this is again like a sequential a sequence of several convolutions and so on, and finally there is like there is there are some skip connections also, and then there are the these other modules. So all these modules like so basically they make a like a very detailed pipeline in which say all these modules are deployed, some in serial and some in parallel. There are all these skip connections, etc., etc., and finally the output is like given an input image like this, which is a like which is obtained from a city, like which is basically an image captured, an aerial image captured over the city. The output is that like this kind of a segmented map. So here you can see the different like as this suggests, the different colors they indicate different like different categories of things in the city. So these green things, these are the road, these pink things, these are the green regions here, the like we can say some kind of parks, and then there are these buildings which are shown in this sea green color, etc., etc. And so for the different these are the different classes which they are looking for: the nature, the residential areas, the driving areas, parking areas, etc. So like each of the like in the output, each of these categories are to be indicated by some kind of by like is to be represented as a cluster or indicated by a color, and that is what they have done. Now because there are so many categories and subcategories, that they need this kind of a like a high very involved structure with so many like sequential and parallel connections, skip connections, etc., and many of these connections like there are lots of modules hidden between them as shown here. So this also the another important thing here is that so the training data was collected by a helicopter over the city of Munich, which is in Germany. Total took a 16 images. So these were all like very high resolution images, as you can see, like 5616 times 3744. This is obviously at a much higher resolution than the images which we normally deal with when the natural images which we take on our cameras and so on. And you can, as you can see here, the resolution is like 13 centimeter per pixel. So every pixel is this in this image, it covers a 13 centimeter by 13 centimeter area. So you can imagine how high resolution or how high quality these images are. That is the like even from a high altitude, it is being able to capture almost a centimeter by centimeter like map of the whole thing. But the idea is that they have taken this image over Munich, and because there are only 16 images, like they can actually, and also because Munich is a planned city where we actually have a detailed map of which thing is located in which region, it's possible to do the manual annotation, and then the model can be calibrated according to it by providing the output levels. But once the once the model has been developed, that is all the parameters have been learned and so on, the next step is to deploy it in other parts of the world where we have the imagery but not necessarily the labels. So they have, in this paper they discuss how the model which they have learned on the basis of the Munich data is actually applied on the different on many cities in different parts of the world, in different countries, different continents and so on, and they find that the proposed approach it gives the results which are very similar to the ground truth in each of the cases, and the results of the proposed skyscape net, this is much closer to the ground truth than alternative approaches to image segmentation. Similar, there is another task here. This is this is talking about identifying flood water. So like we know that like inundations and flooding takes place, especially in urban as well as rural areas. So the task here is take from the satellite imageries, identify where all floods have happened. So this is so there are two tasks here. One is the bigger task is water detection, and the second is within the regions which are found to have water, then to separate them, like either the like either the stagnant water or the permanent water or the flood water. That is, of course, there are rivers and seas which always have water, so they are not to be considered as flooding, but then there are also like other regions which usually do not have water, but at a particular moment they may be having water. So that is an example of flooding. So for that purpose also they have developed this kind of a neural network. So here actually the aim is not so much to come up with a new architecture. In fact, they have not done that. They are focusing on a rather simple fully connected neural network only, but the questions they are asking is different. So usually this kind of flood water detection is done using some kind of a based on some kind of threshold of something known as backscattering. So like the source of the data is from the MODIS satellite, where images are captured in the NIR, which is the near infrared bands, and so now water detection can also be done on SAR images. Now the challenge here is these inundated objects, and the identifying the flood water is often difficult, because the water is it's not that the flood water is always present as water. Many other things are immersed in it also. I mean, various objects may be floating in it, or like suppose there is a building around which water has accumulated. So like that, separating the water from the building, that might often be a difficult task, and so on. And even bigger challenge is to distinguish between flood water and permanent water. So the data set which they have obtained, so there is again this time also there is a challenge like this. So they have, on the basis of that, they have captured like a georeference data set which has 4831 images. Each image is 512 cross 512 resolution, and these are of different 11 distinct flood events, and so on this they have to train their model. And now they also have a separate data set for water versus non-water classification. So once, as I said earlier also, the one task is water versus non-water classification, for this they have built a neural network based on some data set where only the water has been where the aim is just to classify each pixel of whether it is water or it is non-water, and then based on that they have to build another neural network which especially for the water pixels, it has to classify whether it is permanent water or flood water. So again, it is seldom possible to do it based on one individual pixel. It is necessary to take the context into account. By context I mean the spatial context. So like if it turns out that so many other adjacent pixels also have water, then probably it looks like permanent water. But if there are some like various non-water things present in it, then it might be flood water. Now if we have a time sequence of such data, then like identifying flood water might become more easy, because the flood water is not present all the time, but permanent water is by definition present in it should be present in all the images. So the main question here are of this particular study that we showed, these are twofold. One is that can deep learning at all beat the threshold based approaches for this flood water detection? So as I said that there is this the approach called backscattering. So by the way, this map actually shows the different locations from which the water data set has been created. Now it's traditionally this is done by backscattering, by measuring the or putting a threshold on a quantity known as backscattering, which can be measured on the basis of remote sensing imagery. So the one question is whether deep learning can beat that method, and the second is weak labeling possible? That is to say, do I need to label each pixel by saying that this is flood water, this is permanent water, this is not water, etc., or is it enough to have weak labeling, that is for every image I just say that this contains flood water without specifying exactly which pixels have. and so these are some of the results which they have shown. And so they have measured these omission and commission errors, which are basically equivalent to precision and recall, and they have shown that the results are actually mixed. It's not that like the proposed neural network does well all the situation in all cases. In fact, they find that as far as detecting permanent water is concerned, it's really the threshold based backscattering method that often does well, at least in terms of omission error. But though for commission error, I think these some proposed neural networks can be effective. However, for flood water, the threshold based approach is, or I mean for separating flood water, this threshold based approach is often found to be lacking, and in such situations the neural network may do a better job. So that is the and then finally there is one more paper which is about sea land segmentation from remote sensing images. So this is also based on UNet. So the task here is to separate so this is again, as you can see, this is again has the UNet kind of structure with multiple skip connections like this, and so one important aspect or one important addition they have made on top of it is something known as identity mapping. That is, in the last block of UNet, they have basically made a dense block which has 6 convolutional layer, and it has these kinds of short connections, so like which they are calling as identity mapping. So this identity mapping is again nothing but this kind of skip connection which are used, and once again to maintain the kind of consistency. So there are, first of all, there are these large skip connections across the different convolution layers and so on, and then here within the same within the same, we can say the same resolution, there are further skip connections. So here a like every convolution is succeeded by some kind of a pooling, that is to reduce the resolution, as you can see, till it reaches some kind of a base resolution, this 20 cross 20, after which the resolution is again increased step by step. So this happens by pooling and like unpooling, and from the and as discussed earlier also, there are these skip connections from one level to another, and then after they reach the back to the original resolution, they have another round of this kind of what they are calling as a dense block. So here there is no pooling, there is only a sequence of convolution operations, and then across these convolutions also there are the skip connections. And so this is like used for the mapping, the land sea classification. So the every pixel here is to be segmented. I mean, these kinds of images which are mostly over the coastline, they have to be segmented to specifically show which pixels are the ground and which or the land, and which pixels are the sea. And as you can see, these coastlines are often very complicated, that is, it's not a straight coastline, they are very much broken, and you can see some inlets of sea into the land, some inlets of land into the sea, and so on. So it turns out that so this is the ground truth, and it turns out that the proposed method which contains all the so originally there is the UNet, and then there is what they have proposed here as the residual dense UNet. So that is UNet containing this additional layer which I just discussed, and it turns out that like providing this dense layer, this actually performs somewhat better than UNet on this particular task. So these are the references for like for the different image segmentation problems that we discussed today. So basically the message is that like the concept of image sensing, image segmentation, this has multiple applications in remote sensing, and like these various neural networks and deep learning models starting from UNet, but with various sophistication added to them as specific to the different tasks, they help to improve the performance for those specific tasks. So that brings us to the end of this lecture. Thank you, and we will continue our discussion on how machine learning can be used for remote sensing in the previous lectures. So till then,